Welcome back, friends. In the Fourier transform, the next very important thing is distortionless system or distortionless transmission. Distortionless transmission. So let's see. If I take a system, LTI system, I want to say this system is a distortionless, not a LTI system, any system if I take. I want to say this system is distortionless. How can I say this system is distortionless? First of all, you have to understand what do you mean by distortionless system. That means, suppose if I have input, one waveform, whatever the waveform is, I don't know, one waveform, then output has to be the replica of the input. That means it may be, size may change, maybe it may be attenuated or it may be amplified, I don't care, but it has to be replica. That is the one thing. And it may have some finite what we can say delay. That means if any signal is passed through the system, if the input is given, at the same time I cannot get the output, after some delay I can get the output. So that's actually happening. So that is called as propagation delay. So if the system produces replica of the input with some delay is called as distortionless system, or the transmission is called as distortionless transmission. That means if I say x of t is the input, now I have to get y of t, which is k times x, that k value greater than 1 or less than 1, so depending on the system, t minus t naught, t minus t naught. So this may be delayed by t naught and it may be attenuated or it may be amplified by a factor k. So I don't know, but I can call this system is a distortionless system. If a system behaves like this, then we can call it as a distortionless system. So we got y of t is kx of t minus t naught. So I can say distortionless transmission system. What is the system? It produces the output which is a replica of input. Replica of input and with some delay. Then we can call it is a distortionless system or distortionless transmission. Now if I say find the Fourier transform on both sides or apply the Fourier transform on both sides, then what we are going to get, y of omega is equal to k x of omega e power minus j omega t naught, j omega t naught. So what is the frequency response h of omega, which is y of omega by x of omega, which is equal to k e power minus j omega t naught. This is also can be written as k at an angle of minus t naught omega. The angle is minus omega t naught, so I can write this one. So here this is nothing but the amplitude spectrum and this one is nothing but the phase spectrum. So if I draw amplitude spectrum, with respect to omega, so it is going to be constant k. It is going to be constant k. Next we are having phase spectrum. Which is like this. phase spectrum is minus T naught omega. That means it is a straight line passing through origin with negative slope. So it is a straight line passing through origin with a negative slope. What is the slope here? Slope is equal to minus T naught. That slope indicates delay. That slope indicates delay. So I hope you understood. This is the amplitude spectrum. This is the phase spectrum. So in short, what we can say, for a distortionless system, the amplitude spectrum must be a constant and a phase spectrum must be a linear variation with the frequency. It has to be linearly varying with respect to frequency. That's what the meaning of it. Clear? Take it. So just I am explaining these things in word form. Conditions. For distortionless system. Conditions for distortionless system. The first condition, amplitude spectrum must be constant. Must be constant. So you may get down, sir, what do you mean by amplitude spectrum or magnitude spectrum is constant? That means that is all the frequency components are scaled by the same constant, that is nothing but k. All the frequency components are scaled by a constant k. Constant k. Suppose if this condition is violated, then we can say the system is introducing amplitude distortion, or we can say frequency distortion. This is also called as frequency distortion. If this condition is not satisfied, this condition is not satisfied, then the system introduces amplitude distortion or frequency distortion, or frequency distortion. We can call it as amplitude distortion or frequency distortion. Next, second, then we have to say phase spectrum. Phase spectrum must be linear function of omega with a negative slope. So there is no way we can get a positive slope. What do you mean by positive slope? So this is going to be positive slope. That means we are getting the signal advanced. That means without giving the input, I am getting the output, which is not a possibility. Clear? So we should get only negative slope only. That's the one thing. And let's say, what do you mean by linear function of omega? So if it is having constant slope T naught, that means minus T naught, that means it is producing same delay for all the frequency components. That means suppose the signal is having, let's say, 2 frequencies. Now for each frequency we are having the same delay. That means if I send this signal, so both the frequencies reaches the output at the same time because they are having the same delay. Now if it is not a linear function of omega, then what will happen? We are having, that means it is not a constant slope. So that means we are having a different delays for different frequencies. That means at a time I am not going to get the output. I am going to get the output of different frequencies at different instants of time. So which is going to be distortion. So that is distortion is called as phase distortion. That distortion is called as phase distortion. So I can say phase spectrum must be linear function of frequency. Linear function of frequency. Linear function of frequency. That is, all the frequency components are delayed by same time t naught. Same time t naught. If this condition is violated, then we can say the system is introducing phase distortion. Phase distortion. Phase distortion. So this is about the amplitude can be determined. Distortion can be determined by two parameters. One is called as phase delay, and another one is called as group delay. So first let's say, what is a phase delay? Phase delay means, suppose a signal is passed through the system, then how much is the delay which is produced in the signal, then that is called as phase delay. But here the condition is the signal must have single frequency. So if any sinusoidal wave or cosinusoidal wave is passed through the system, how much delay is introduced by the system to that one is nothing but the phase delay. So the phase delay concept is applicable for single frequency. That means input must have single frequency. Single frequency. Then what is the phase delay? So let's say tau p. Phase delay is nothing but minus angle of h of omega naught by omega naught. So that is what the phase delay we can calculate in this manner. Next, group delay. What is a group delay? So if the input signal is having more frequency, then what is the delay for a single frequency in the number of frequencies? Then we can call it is nothing but the group delay. So it is delay given to single frequency component. Single frequency component in group of frequencies. Then tau g is equal to minus d angle h of omega by d omega. This is also slope at omega is equal to omega naught. So this is what it is called as group delay. Now, if we don't have phase distortion, then phase delay and group delay has to be equal and they have to be constant. So if tau p, tau g, that means phase delay and group delay is equal to constant, then we can call no phase distortion. No phase distortion. No phase distortion. So let's see, in the distortionless system, are they going to be the same or not? For a distortionless system, what is angle of h of omega? Which is nothing but minus T naught omega. Minus T naught omega. So let's say, what is the phase delay? That is minus angle of h of omega naught by omega naught. By omega naught. That is minus T naught omega naught by omega naught. Get cancel. Minus minus get cancel. So it is going to be plus T naught. Plus T naught. So this is the delay, phase delay. Then I want to get group delay. Group delay is nothing but minus d angle of h of omega by d omega. So if I differentiate that, this is nothing but minus of minus T naught, which is nothing but T naught. So if you observe carefully, phase delay and group delay are equal, that to a constant, there is nothing but T naught. So it is a distortionless system. So tau p is equal to tau g is equal to T naught. So I can say distortionless system. Clear? So let's take a question. Example. So frequency response is given. So what is the frequency response they have given? With respect to f, kilohertz. Mod h of f, that means magnitude spectrum. (20, 30, 50, 60). Angle of h of f. Okay. So for what range of frequencies? For what range of frequencies there is no distortion? There is no distortion. Okay. I told you, for a distortionless system, we require constant magnitude spectrum and a linear phase spectrum. So if you observe one by one, so up to 20 kilohertz, we don't have the constant magnitude spectrum, but we are having a linear. So I can say here we are having only magnitude distortion or amplitude distortion. Amplitude distortion in this range. Next, Between 20 and 30, if you observe carefully, so we are having constant magnitude as well as linear. So I can say no distortion, no distortion. Next, 30 to 50, 30 to 50. 30 to 50, we are having constant magnitude spectrum, constant phase spectrum. So we don't have the magnitude distortion, but we are having the phase distortion because it is a constant value, phase distortion. Next, between 50 and 60, we are having the constant phase spectrum and it is a decreasing. So both are not correct, both are not required. So distortion, both distortions, both distortion. So where we are not going to get any distortion here, 20 kilohertz to 30 kilohertz. The range is 20 kilohertz to 30 kilohertz. This is the range what we have. Clear? Take it. The impulse response of a LTI system is h of t is equal to e power minus 2t u of t. First question. The frequency response of the system is options 1 by 2 plus j omega, 2 by 2 plus j omega, 1 by 2 minus j omega, 1 by minus 2 minus j omega. The output of the system to a sinusoidal input of x of t is equal to 2 cos 2t is options 0, option B 2 power minus 0.25 cos 2t minus 0.125 pi, option C 2 minus 0.5 cos 2t minus 0.125 pi, two power minus 0.5 cos 2t minus 0.25 pi. Which option is going to be correct? Let's see. Frequency response means h of t is given. What is that? E power minus 2t u of t. Here, frequency response is nothing but h of omega. So for this function, what is the Fourier transform? So if you have impulse response, if you try to find out the Fourier transform for the impulse response is nothing but the frequency response. So which is nothing but 1 by 2 plus j omega. So directly the answer is 2 plus 1 by 2 plus j omega. Next, for this system h of omega, we have given the input is 2 cos 2t. 2 cos 2t. So here the omega naught value is equal to 2. Then we are going to get the output is mod h of omega naught into 2 cos 2t plus angle of h of omega naught. Angle of h of omega naught. So this is what the output. This is what the output. So we just have to know what is h of omega naught angle. So first of all, what is h of omega naught? H of omega at omega is equal to 2. So this is nothing but 1 by 2 plus j2. That is 1 by 2 root 2 at an angle minus 45 degrees. If this function is multiplied with 2 cos 2t, then what is output? Output is equal to 2 into 1 by 2 root 2 cos 2t minus 45 degrees. So I can write this one 2 to get cancelled. Root 2 goes to numerator minus 0.5 cos 2t minus 45 degrees, that is nothing but pi by 4, which is nothing but 0.25 pi. So this is what the output we are going to get. So option D is correct. Clear? Take it. And still we have to do the analysis, little bit analysis. Suppose the next question if I ask like this, for the same question, phase delay for x of t is equal to 2 cos 2t. 2 cos 2t. So phase delay means, so tau p is equal to minus angle of h of omega naught by omega naught. What is h of omega we got? 1 by 2 plus j omega. 1 by 2 plus j omega. So this can be written as 1 by root of 2 square plus omega square angle of minus tan inverse omega by 2. Omega by 2. So here what is the angle? Minus of minus tan inverse omega naught value, which is nothing but 2 by 2. So this is going to be 2 by 2. 2 by 2, which is nothing but 1. So which is nothing but pi by 4 by 2. So this is nothing but pi by 8 seconds. Pi by 8 seconds. So this is the phase delay. Now if I ask, is it having the magnitude distortion? Of course. Angle of h of omega is nothing but 1 by root of 4 plus omega square, which is not a constant. Which is not a constant. Next, angle of h of omega, which is minus tan inverse omega by 2, which is not a linear function of frequency, is not a linear function of frequency, function of omega. So from this I can conclude that it is going to introduce distortion in the system. So sorry, it is a distortion system. Distortion. Take it. Periodic signals also. So give a heading, Fourier transform for periodic signals. Fourier transform for periodic signals. But we cannot directly write Fourier transform for periodic signal. So to write Fourier transform for periodic signal, still we have to know Fourier series. What do you mean by that? Suppose let's say a signal x of t is periodic, then we can write n is equal to minus infinity to infinity Cn e power jn omega naught t. In this way we can write. For this signal I have to calculate what is the Fourier transform. How we can do that? Let's see. Let's see one by one. First, for 1, what is the Fourier transform? 2 pi delta omega e power jn omega naught t. Then we are having 2 pi delta omega minus n omega naught. Next, if it is multiplied with Cn, then Cn is a constant with respect to t, so 2 pi Cn delta omega minus n omega naught. Next, if I take the summation, which is a linearity property, minus infinity to infinity Cn e power jn omega naught t, then we have to take the same summation here also. 2 pi you take out, n is equal to minus infinity to infinity Cn delta omega minus n omega naught. So this is what the x of t, then this is going to be x of omega. So to calculate x of omega, still we require Fourier series coefficient. Let's take one example to make you understand how to calculate Fourier transform for periodic signals. I'll take one example which is impulse train. Let's call it is P of t. Zero, let's say Ts, 2Ts, minus Ts, and so on. So here period is nothing but Ts. Let's say A. Now, what is the Cn value for this function? We already know, area by period. We have seen this. Area is nothing but A by period, which is nothing but Ts, which is a constant value. Then for this one, what is P of omega? Which is 2 pi summation n is equal to minus infinity to infinity Cn, that is nothing but A by Ts, delta omega minus n omega naught. What is omega naught here? 2 pi by Ts. So 2 pi A by Ts summation n is equal to minus infinity to infinity delta omega minus n omega naught. So this is the Fourier transform for impulse train, which is periodic. Clear? Take it. Is convolution in frequency domain. Convolution in frequency domain. What do I mean by that? Suppose if a signal x of t is multiplied with h of t, then in the frequency domain it is going to be convolution, that is x of omega convolution with h of omega, but there is a factor 1 by 2 pi. But in the f domain, x of t multiplied with h of t is directly having x of f convolution with h of f. So this is what we have to remember. So with this property I can conclude the Fourier transform topic. So in the next session we are going to start the sampling, which is related to the Fourier transform only. So once we complete the sampling theorem, then we will enter into Laplace transform. Okay, that's all. Thank you.